about are going to be EtherChannels. Now, EtherChannels, the way, that's Cisco's name for the technology. And for a very, very long time, we didn't have any standardized name for it. But these days, I believe that this stuff is called link aggregation groups. Or just simply link aggregation. So that's the same thing. Or as I believe HP calls them, trunks. So if you are working in a multi-vendor environment, when you are working with the technology that Cisco calls EtherChannels, you may encounter all these different names. But for your CCIE lab exam, it's the EtherChannel name that we care about. Now, EtherChannels are relatively inexpensive way to increase the bandwidth between two switches. But as we will see, this relatively inexpensive way of increasing the bandwidth provides what inexpensive solutions usually do, an inexpensive increase in bandwidth, which means that it's not exactly perfect. So when we have two devices, let's say two switches, switch 1 and switch 2, and we have multiple links between them. By default, if we are running the spanning tree here, one of these links will be blocking and we are not going to be using it. Now, we can go through the acrobatics of spanning tree and try to increase this bandwidth by mapping some VLANs to one link and some other VLANs to other link, and then having different routes on different locations, and we can as well poke our own eyes out and have equal entertainment and success in actually increasing the bandwidth using our network. Or we can bundle these two links in a logical group and make them appear to the spanning tree as if they were actually one logical interface. Now, when we do that, we need to configure both the local interfaces that are participating in an Ether channel, and we have to configure the actual bundle configurations on these two switches. So the configuration consists of physical interface configuration and the logical interface configuration, which in iOS is called port channel. Now, when we have port channel interfaces, it's important to know that they can be either layer 2 or they can be layer 3. The configuration is pretty much the same. But when we are using layer 2 Ether channels, it's very, very important that the configuration on the physical members and on the port channel interface actually matches. On 3560 switches, we don't have the problem of mismatch of features on the physical interfaces, but if you're using some other switches in, say, production environments, you need to make sure that the actual physical characteristics of the interface match. And by physical characteristics, I mean, for example, queuing capabilities. One of the horror stories that I remember from my past life when I was actually working in production environments was trying to set up a port channel on a 6500 switch, and members were on two different line cards that have different capabilities. So they were both gigabit ports, but different queuing capabilities. One had more queues than the other and different capabilities, and simply the port channel wouldn't come up because it was complaining about the QoS capability mismatch. So on 3560 you don't have this problem, but it's important to remember and important to mention that you can bundle only the interfaces of the same speed. That means that we can only bundle 2 fast Ethernet interfaces, or 4 or 8, whatever, but we cannot bundle 1 fast Ethernet interface and 1 gigabit interface. That will never work. So the interface speeds must match to make this configuration. Also, when configuring Ether channels, especially in the lab environment, when you could be asked to configure a large number of Ether channels at the same time, remember, this is pretty much the topology that you will have in your lab. And if they ask you to build Ether channels on all of these pairs of links here, what might happen is that you are building relatively large number of these port channel interfaces at once, and in my experience, sometimes the switches get a little bit confused and you end up having all sorts of inconsistent states with Ether channels. This is the reason why I'm going to show you my preferred way of configuring Ether channels, which may or may not apply in real life because it's a little bit disruptive the way I do it, but in the lab environment where nobody cares if some links go down actually, it would be a preferred way because it is, in my experience, something that provides you with the most reliable way of configuring Ether channels and making sure that they are actually up and running after you're done with them. So my steps for configuring Ether channel is to first configure physical interfaces, and this is where I start by shutting them down, then configure them as trunks, access ports, or layer 3 ports, make sure that all of them are configured properly. Then I reference the channel to use, and here I'm going to decide on the protocol. Am I going to use LACP? Am I going to be using PAGP? Or am I going to be using just the mode on, the static configuration of the Ether channel? Then, number 2, I'm actually manually going to configure the Ether channel interface. Make sure that my layer 2 settings match, and then finally I'm going to go and enable, so let me be a little bit more specific there. So these are the steps that I'm going to follow every time I'm configuring Ether channels. So I'm going to start by configuring the physical interfaces. I'm going to start by shutting them down, going to configure them as trunks, access ports, layer 3 ports, whatever I need to do there, all the configuration that needs to go there, allowed VLANs, native VLAN, whatever needs to be done, I'm going to do it on the shutdown port. Going to configure the channel group reference from the physical interfaces. When that is okay, I'm actually going to go and manually configure the port channel interface, which in many cases it's not required, because when you reference the port channel group from a physical member, the port channel interface should have been automatically created. And that's the key point, should be created. It might or it might not. I mean, I've seen all sorts of weird things in iOS in my life. So I'm not going to leave anything to chance. I'm going to create that port channel interface manually myself, configure it so that my layer 2 settings match. Whatever I'm allowing on the physical interfaces, I'm going to allow on the port channel. If they are trunks, I'm going to make sure that the port channel is trunk. Just make sure that all this is in place. And when I'm happy with that, I'm going to go to the physical interfaces and bring them up. After that is done, I'm going to verify the operation of my port channel interface, and I'm going to run very simple command for that. So just as an exercise now, what I'm going to do is I'm going to have 2 of my switches, switch 1 and switch 2, and I'm going to have 2 connections between them. So this is going to be port 23 and 24, and I want to build an Ether channel between them. And for this purpose, I'm going to be using LACP as the grouping aggregation protocol there. So here I have my cat1 and cat2, and these are the same configurations we had yesterday, so I have not really changed anything since yesterday. So we do have some pre-configuration on these interfaces. And let's say that I want my port channel interface to actually match this exact configuration. So let me just fire up my text editor here. So what I'm going to do now is I'm going to make sure that my interfaces, Fastnet 23 and 24, have the same configuration. So I'm just going to copy this in. Now, I don't know what is the configuration on port 23, so there is one thing that I can do there. So I'm just going to default the configuration on it. That is going to return it to whatever is the switch default. Going to shut this down. And here I'm going to say channel group, let's say 12 mode active. This will enable LACP on this interface. Then I'm going to say interface port channel 12, and I'm going to repeat the same configuration here. And then finally, when I'm happy with that, I'm going to say no shutdown here. So this would be the process that I would do every time when I'm configuring port channels. Oops. Yeah, okay, on the port channel itself, this is irrelevant command, but again, iOS simply complains that there is an error there, so it's really no harm leaving it in copy paste. You know, I saved myself a couple of seconds not removing it, but anyways, it was a tiny little mistake in there. So going to do the same thing on Cat2. And if I remember well, there we had some native VLAN mismatch, but let's fix that. So I'm just going to create VLAN 40 on Cat2. I forgot about that example that last night we left it off with that native VLAN mismatch on 2 trunks, so I have corrected it. So this is now the configuration on our Cat2. So let me just delete those SVIs that we had yesterday as well. So right now, I am of the opinion that the Ether channel is operational, but I don't know that. I think I configured it right. So let's take a look. So what I'm going to do is show Ether channel summary. And here, what I'm seeing is that I have group 12 that is using the port channel, the logical interface port channel 12, and I can see that it is actually layer 2. So this S stands for layer 2, and I can see U, which means that it is actually in use. Where is U? There it is. So this SU here tells me that this is okay, but I want to verify the rest as well. Here I can see that the protocol is LACP, that's exactly what I wanted. And here with the physical interfaces, I can see this uppercase P, which basically tells me that interfaces are bundled in the port channel. That is very important because sometimes you might see that they are waiting to be aggregated. This is usually not good news. And you can also see that they are standalone. Let me see, there it is. If you see I, that is also not very good, because that means that we are not actually managing to get the Ether channel operational. But this is how things look when everything is okay. Now, mind you, there are other show Ether channel commands. For example, you can do show Ether channel detail, which will show you a lot of detailed information, but some of this information is actually incorrect. Believe it or not, some of the information in this output is not correct. And one of my favorites is this one. So let me show you that. There it is. So we have 2 ports here, 23 and port 24. Now, one of these interfaces is what is called master in the bundle. And if you take a look at this output, if we first take a look at this, Fast Ethernet 23 is now telling us, hey, I am up and I am master in the bundle. If we take a look at Fast Ethernet 24, Fast Ethernet 24 is claiming to be the master in the bundle. That is not true. Only one of them is the master in the bundle, and in this case, it is going to be Fast Ethernet 023 because it will always be the lower port number. Just to give you an idea, on 3560, the lowest port numbers are gigabit 00 interfaces, sorry, gigabit 01, then 02, and then all the fast Ethernet interfaces in sequence. So this is the order of preference, or this is the order of port numbering in Catalyst 3560, and this is significant for Ether channels for determining who is the master in the bundle, and it is also significant for the spanning tree when certain spanning tree decisions are made, because we are looking at the lowest port ID, and port ID is determined based on this, which is the lower value of the internal port identifier on the switch itself. So what does the master in bundle do, and why is it important to understand what it does, and why is this particularly annoying to me? here is that mastering the bundle, so let's say that this is our port 23 on this side and port 23 on this side. They don't necessarily have to match, but they usually will. The mastering the bundle is the port, the physical port member that will be sending spanning tree frames. So spanning tree in this case, because this is perceived as a single logical interface from the spanning tree perspective. And we can actually see that if I go to Cat1 and if I do show spanning tree, again, just a reminder, we converted the spanning tree from the default per VLAN spanning tree to the MST. So we are going to be seeing the MST output here. We can see here that we have FastEthernet 01, a standalone interface on the device, and FastEthernet 03 that are simply saying that they are designated ports, but we cannot see ports 23 and 24. We are seeing the port channel interface, because from the spanning tree perspective, this is one interface. But in that one interface, some link needs to send spanning tree frames, needs to send the BPDUs. And in this case, it will be port 23, because that is the port that is mastering the bundle. That is the one that is actually sending the spanning tree BPDU frames. But if you take a look at this output here, show EtherChannel detail, for example, they're both going to be claiming they are the master in the bundle. So this is why I think that when you are in the lab, stick to simple commands. So for example, show EtherChannel summary. It will show you pretty much all the information that you will need to verify that your EtherChannel is operational. All other commands may or may not show you correct information. Like for example, show EtherChannel port is the very similar command to show EtherChannel detail. A useful one would be, for example, show EtherChannel load balance to show you which is the load balancing algorithm that is actually in use by the switch right now. But other than show EtherChannel summary on show EtherChannel load balance, I suggest in the lab environment, in the lab day, during your CCIE lab exam, stay away from those commands because they may not be showing you correct information. This is the basic of the EtherChannel. Now, when we start diving a little bit deeper in EtherChannel, we have to remember that there are, generally speaking, three ways of configuring EtherChannel. We have LACP, we have PAGP, and there is a static on configuration. Now, LACP is a standard, PAGP is Cisco proprietary, and mode on is a headache in making. Now, why do I say it's a headache in making? Now, I say that because this is by far everyone's favorite. And this is by far the easiest way to cause a complete meltdown in your switch network. Because you are forcing an EtherChannel on one side, if you are not having the same configuration on the other side, you might have a situation in which you create a bridging loop that there is nothing to prevent, and bridging loops are a very, very bad thing in your network and are best avoided. Now, unless you are absolutely compelled and forced to use mode on, which basically means if you're running older versions of the VMware in your network, don't use on. If you are forced and compelled to use mode on, use it, but be on a lookout, because you need to be absolutely certain that EtherChannel is configured on the both sides. Because when you have mode on configured on one side and you have standalone ports on the other side, think about what's going to happen in spanning tree. One of these ports here will actually be designated, will be sending BPDUs, the other one wouldn't. So this one here, let's say that the root is on this side. And let me actually use the whiteboard, it's easier to explain that way. So let's say that we have two devices, okay? And we have two links between them. On this side here, I have configured EtherChannel, but these are standalone ports on this side. So there is no EtherChannel configured on this device. So we have switch 1 and switch 2. Now, let's say that this was mastering the bundle and that the root is either this switch or somewhere behind this switch. That means that our BPDU frames will be sent out on this port. This becomes a designated port. Well, actually, from the perspective of this device, what is designated port is, so our spanning tree frames are being sent out this way, and our designated port is actually a port channel. So this here is going to become a root port. But because we are not receiving any BPDU frames on this port here, from the perspective of switch 2, is going to become a designated port. So we might have traffic that is being sent this way and then sent back this way, right? Which means that we have just created a loop in our network. And if you have this in maybe multiple locations, what you might have is a real endless loop of traffic. And this is not a very nice thing to have. And the root cause of this problem was that we used mode on this side here. So this is why I suggest, unless you are compelled to use mode on, don't use it. In the CCIE lab exam, if they don't tell you which aggregation protocol to use, stay away from mode on, because you can by accident actually create this scenario and you can have really bad day in the lab after that. Stick with PEG-P or use LACP if they don't tell you otherwise. If they tell you use mode on, well, in that case you are going to use mode on. But if they don't tell you, stick with one of these two. In real life, again, depends on the requirement, but my recommendation would be, if you are not compelled to use something else, use the LACP. Now, LACP can operate in two modes. There is an active mode and there is a passive mode. Now, as the words imply, in active mode, the side that is configured as active is actively going to negotiate the formation of the bundle. The passive side is just going to wait there to receive the LACP frame so that it can respond to them and actually form an ether channel. With PEG-P, of course, Cisco had to be different than anyone else. We have desirable and we have auto. Just like with DTP, so the naming is the same as with DTP, but please do not mix this with DTP because they are very different. So I'm just going to give you that warning. Do not mix with DTP naming. Now, mind you, DTP and PEG-P can coexist on the same link. So that's not what I mean by don't mix. They can be on the same link, but it's important that in your mind, even though the names for modes are the same, to not mix them up. So when you see desirable, it's not necessarily DTP that we are talking about. It could be the configuration for PEG-P. So you have to look in which context the word desirable or the word auto were used. And just like we did for DTP yesterday, let's see ether channel formation combinations, in which cases we are going to have successfully formed ether channel. So my possible options here are to have active on one side and active on the other side. Then I can have active on one side and passive on the other side. I can have active, desirable, active, auto, active, on. Let's see what's next. We have passive, passive, passive and desirable, passive and auto, passive and on. Then we have desirable, desirable, And I have to admit, this is the first time in my life that I have actually managed to fit this on a single page. So let's see. Now, if I have active and active on both sides, the Ether channel will be operational. So we are going to be okay on this side, and we are going to be okay on this side. If we have active and passive, this is a valid configuration, and it will be okay. When we have active and on, the Ether channel will be inoperational, and on both sides we are going to have the same situation. If we have active and auto, the same situation, and Ether channel will actually be inoperative on the link. If we have active and on, we are going to have an unusual situation that the active side is going to think that the interfaces need to be standalone, but the on side, of course, is going to think that Ether channel is on. So technically speaking, the Ether channel is inoperative, but this side here is in danger of causing the loop in our network. If we have passive and passive, the situation is that we do not have an operational Ether channel, but this is not a dangerous situation because both sides will agree on this. If we have passive and desirable, again, this is misconfiguration, which will cause the Ether channels not to be operative, but it's not a dangerous misconfiguration. We are going to have standalone ports that function normally. Passive and auto, same situation. Passive and on, again, this is a mismatched in configuration, but this is a dangerous situation because this side here will think that we are an Ether channel. If we have desirable and desirable, this is a valid configuration, and we are going to have operational Ether channels, so are desirable and auto. If we have desirable and on, again, this is a mismatch in configuration, so Ether channel is technically speaking inoperative, but the on side thinks this is an Ether channel and is in danger of creating loops. Auto, again, this is a valid configuration that will cause the trunks not to be, that will cause the Ether channels not to be operative, but there is nothing dangerous about this combination. Auto on, again, mismatch in configuration that will cause the Ether channel not to be operative, and the loop can form. Here, if we have on and on, this is a valid configuration and Ether channels will be operational. So in these cases here, we are going to have a fully functioning Ether channel. So where are they? Here are they. So these are the only valid combinations. Now, mind you that when we talked about DTP yesterday, and this is why I said it's important not to mix these two up, a perfectly valid configuration was to have desirable on one side and to have on the other side. And this would have resulted in an operational trunk with DTP. But for PAG-P, this is not a correct configuration because nothing will be actually responding to our PAG-P frames, to the negotiation frames on the other side. So we are going to have a mismatched configuration in this case here. So this is the formation of Ether channels when you are using different protocols. Now, when we talk about Ether channels, it's important to understand how load balancing in Ether channels work. Now, I'm going to start by saying there is no load balancing in Ether channels. There is actually load sharing. Because load balancing would imply that same traffic could be sent either over link number 1 or link number 2, depending on what the load is, so that we are trying to somehow balance the load. This is not what happens because the load sharing in Ether channels is actually deterministic. The same traffic kind will always take the same link. Now, how do we identify the same traffic? This is where different load balancing mechanisms or load sharing mechanisms come into play. Now, I like to divide them into two categories. We have simple ones and we have complex ones. Now, the simple ones are using just a single piece of information to provide load balancing. These are the source MAC load balancing mechanism, source IP, destination MAC and destination IP. Now, more complex ones are source destination MAC, which take two pieces of information into account, the source and the destination address. It's source destination IP, and on some switches, so this is not on 3560, we have source destination port. So when port numbers are actually taken into account as well. So I'm just going to say that this is not available on 3560, but I just included it here because you might actually encounter it. Now, if you are using any one of these load balancing mechanisms, that means that the traffic that has the same source MAC address or same source IP address or destination MAC or destination IP, whichever one we are using, same traffic will always take the same path. What that means is that if we have the traffic, if you're using source MAC or source IP, all the traffic generated by that one host will always take the same physical path. Same is true for these complex ones, because it's the same story. If we have the same combination of the source and destination MAC address, that means the traffic will go the same way. Now, why am I telling you this? Because there are situations, or there could be situations in the lab, when they don't tell you which load sharing algorithm to use, and you need to choose the best one. So here is one example, for example. Let's say that we have two switches, so switch 1 and switch 2, and we do have an ether channel between them. There is a router here, and let's say that this is your router 1, which is connected to the backbone. Now, backbone is just a device under Cisco's control that you don't have access to. And in the lab scenario, they tell you that this is your internet connection. That means internet is there behind the backbone. And here you have router, let's say R2, behind which you do have some hosts. Now, the hosts won't be there, but this will be a pretend scenario. So they're going to tell you that there are some hosts behind R2 on subnet, whatever. Let's say that this is gigabit 00 port, and they are going to tell you that behind this gigabit 00 is where your clients are. And they're going to tell you, make sure that the traffic between switch 1 and switch 2 is using the load balancing mechanism that makes most sense for this scenario. Now, if we go back to the terminal, and if I do show ether channel load balance, I will see that by default, the load balancing mechanism is the source MAC address, which means that when this traffic from these hosts is sent, so let's say that there is a host here that actually sends the traffic, it's going to arrive here to the switch, and it's going to come to the ether channel. Now, the switch 1 needs to sort this traffic based on the source MAC address of this traffic. So at this point, what is the source MAC address of this traffic? It's not the host. The source MAC address will be the MAC address of R2's interface, which means that this traffic, let's say that it gets sorted onto link number 1. Now, let's say that another host here is sending the traffic. When this traffic arrives here, because it's coming from the same MAC address, it will be sent over this link here, which means that in the direction from R2 to the internet, we are never going to be using the bottom link. Now, let's see what happens with the return traffic. There is return traffic coming in. So something from the internet is sending the traffic here. And on switch 2, we are again using the source MAC address for load sharing, which in this case is going to be the MAC address of R1. So this traffic now gets sorted into one of the links. If you are really unlucky, this is going to get mapped to the top link, which means that this link here is completely useless and does absolutely nothing. So in this case, it would make perfect sense to change load balancing mechanism to source destination IP or source destination, or just source IP or destination IP. But anything to do with MAC addresses simply gives us very, very little seed to go under. It gives us very little entropy. Now, the problem here is, and some of you might be thinking, but why doesn't he use source destination MAC? Well, I'm not going to use source destination MAC, because if I use source destination MAC, I will be using this information and this information here, which will always result in the same link being used. Again, I'm not going to gain anything from the other link. And this is just one scenario in which they might tell you, okay, use the most appropriate load sharing mechanism.